Here's the warm-up activity for our next lesson on concavity. So let's go ahead and take a look at these problems to get our brains going for today. Number one, it says, what is the absolute maximum of f of x given that f of x is negative x to the fourth over 4 plus x to the third over 3 plus 3x squared minus 10. So we're looking for the absolute maximum here, okay? So in order to find absolute maximums, we have to go through and find all the critical points and then determine which critical point produces the highest value. So to find critical points, we're going to have to take the derivative here. So f prime of x is equal to, we're going to treat that as a coefficient, so it's negative 1/4 here. So negative 1/4 times 4 is negative 1, x to the third, and then same thing here, plus x squared plus 6x. So that is our derivative function. In order to find critical points, we're going to set the derivative equal to 0. And so when I set this equal to 0, actually before I do that, let me go ahead and factor this. So then we would rewrite this as f prime of x is equal to negative x times x squared minus x minus 6. And then we can keep factoring this. So f prime of x equals negative x times x minus 3 times x plus 2. Okay, so that's the factored form of f prime. Now we're going to look for critical points. So we're going to set the derivative equal to 0. Again, I know that you may be able to do all this in your head all at once, but the idea on the AP exam especially is to be able to express yourself well. The person that's reading the exam, the person that's reading these assessments should be able to follow your logic from step 1 to step 2 without trying to figure out what's going on in your brain. They should be able to see what you're thinking by reading exactly what you're writing. And so we're looking for critical points by setting the derivative equal to 0. That happens when x equals 0, when x equals 3, and when x equals negative 2. So that's one set of critical points. Remember, another set of critical points is when the derivative does not exist. Since this is polynomial, the derivative always exists. And in this case, it doesn't give us any kind of interval or domain, so therefore we don't have any critical points at endpoints. So our critical points, our three critical points are these exactly, x equals negative 2, 0, and 3. Now from here, I'm going to go ahead and draw a number line to get an idea of what's going on. So negative 2, 0, and 3 are all x values, and we're going to figure out what the derivative values are for points within the intervals in between. So we know that the derivative was 0 at those 3 points. Now we're gonna plug in numbers on either sides of those. We could actually skip this step when we're talking about absolute maximums because we're not looking for relative maximums. We're not looking for relative extrema, we're looking for absolute extrema here. So we could, if we wanted to, just take these 3 values and plug them back into the f of x function to see which one produces the highest value. And that might be the most efficient way of doing it. Another way is to maybe try and eliminate some of these values as potential candidates for absolute maximums, because if they happen to be relative minimums, then they can't be maximums. So let's go ahead and plug in a negative 3 here. If I plug in negative 3 to my factored form, I end up with a positive, and a negative. So we know that the derivative is negative for all values less than negative 2. We'll plug in negative 1 in between there. So negative 1 produces positive, produces negative, produces positive. So did I do something wrong here? If I plug in negative 3, I get a positive, I get a negative, and I get a negative. Oh, yeah, I did. So this is positive here in that interval. And then if I plug in negative 1, I get a positive, negative, and a positive. So that's going to be negative. If I plug in 1, I get a negative, and a positive, so that ends up being positive there. And if I plug in a 4, I'm going to end up with a negative, a positive, and a positive, so that'll end up being negative there. So there's our intervals for f of x, for which f is increasing, decreasing, increasing, decreasing. So we can see from there that when x equals negative 2, we have a relative maximum, and when x equals 3, we have a relative maximum. So that might reduce the amount of work that we have to do for this particular problem, because at x equals 0 we have a relative minimum, which means it can't be the absolute maximum. So now from here, we're just going to go ahead and plug these values in to our original f function to see which one produces a higher value. So f of negative 2 is going to be negative 2 to the fourth over 4 plus negative 2 to the third over 3 plus 3 times negative 2 squared minus 10. I'm running out of room here. Minus 10. Let's see, 2, 4, 8, 16. So we end up with negative 16 over 4. We end up with negative 8 over 3. And then we end up with 12 minus 10. So whatever that works out to be, I'm just going to call that f of negative 2 for now. And then simplifying f of 3, figuring out what f of 3 is, that's going to be negative 3 to the fourth over 4 plus 3 to the third over 3 plus 3 times 3 squared and then minus 10. And that'll simplify to negative 81 over 4 plus 27 over 3 plus 27 minus 10. Once you know what f of negative 2 and f of 3 are, you can simplify those, and whichever one ends up being the higher value ends up being your absolute maximum. And remember, when you're talking about absolute maximums, in this case it says what is the absolute maximum. So we don't care about where it occurs. We don't care about the x value for which it occurs at. We care about the absolute maximum value, so we care about the y value. Sometimes the questions will say, at what x value does the absolute maximum occur? Then your answer will be either negative 2 or 3, whichever one ended up producing higher. But in this case, it says, what is the absolute maximum? So we want the actual y value. For number 2, this is going back a little ways here. We're just looking for the derivative in respect to x of cosine squared of pi x over 3. So we're looking for the derivative of that function there. Well, we see a lot going on here. I'm going to first rewrite this to be the derivative of the outermost thing of this function is the squared. The last thing we're going to do in the order of operations here, in the order of things to do, is to square a result after the cosine. So I'm going to go ahead and rewrite this as the cosine of pi over 3x, and then all of that is going to be squared, and then we'll take the derivative of that. So these two things are equivalent here, and the reason I do that is so that I can see what is the inside, what is the outside, so we can apply the chain rule correctly here. So we see that the outermost function is the squared function, and then the next function inside of that is our cosine function, and then inside the cosine is the pi over 3x. So when I go ahead and take the derivative of this guy, I'm going to take the derivative of the outermost thing first. The outermost thing here is something squared. Something squared. So the derivative of something squared is 2 of that something. Okay? So this is just the derivative of the something squared. Okay? Then we multiply it by the derivative of that something, the derivative of that inside thing. So now we're looking at what is the derivative of the cosine function. Well, the derivative of cosine is going to be negative sine of whatever you're taking the cosine of. So it's negative sine of pi over 3x. And then we have another chain because we have something inside the cosine. The derivative of the inside of cosine, the derivative of pi over 3x, is just going to end up being pi over 3. And so we can simplify this a little bit by rewriting it to say negative 2 pi over 3, just putting that constant out front, times the sine of pi over 3x times the cosine of pi over 3x. And so that is our derivative of our given function. So stick around for the lesson on concavity. This is actually kind of a neat way to relate all of the different derivatives, f, f prime, and f double prime.